Welcome to Labster's Electrostatics Lab. Here you can learn about Coulomb's law and study how electrical charges interact with one another. I'm thinking of painting my case a new color this season. I want one of those holographic finishes the cool drones get with powder coating. Powder coating doesn't use any paint. Instead, the powder sticks to the surface thanks to electrostatics. So I want to review the central law of electrostatics, Coulomb's law. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer, such as music, sound effect, voice, and screen reader in accessibility mode. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect, then let's get started with your first mission. What? An instrument is sparking? Perhaps we should take a better look. Take a closer look at the sparking instrument. Oh, how convenient. This is a setup commonly used to demonstrate Coulomb's law. Coulomb's law describes the electrostatic force between two charged particles, the simplest case of an electrical force. It can explain the force between charged spheres, like the ones we have in front of us. We can use this setup to investigate Coulomb's law and the electrostatic force. Like every other force, the electrostatic force has a magnitude and a direction. First, we'll study its magnitude, and we will talk about its direction later. But before we start, there is something I'd like to ask you. Is it a good idea to touch electrical instruments you are unfamiliar with? Good, we are clear on that. Touching any electrically charged objects can be dangerous even at low voltages. You should never touch electrical instruments without qualified guidance, or you will put yourself and others at risk. Where were we? Yes. Let's investigate Coulomb's law using this setup. Here we have two charged spheres. The magnitude of the force between them depends on their charges and the distance between their centers. These are all shown on the screen to your right. I suggest we change a few parameters and see how that affects the electrostatic force between the spheres. First, use the buttons at the base of the ruler to change the distance between the centers of the charged spheres. Then, hit the record button on the monitor to your right to record your measurement of the electrostatic force at that distance. Once you have recorded 3 different data points, we will obtain a tendency line. Record 3 values of the electrostatic force for 3 different values of the distance. Well done! You have obtained a graph of how the magnitude of the electrostatic force changes with the distance between the centers of the charged spheres. It will be saved to your media tab so you can look at it whenever you want. We have seen how the strength of the electrostatic force changes with the distance between the center of the spheres. Now, let's see what happens if we change the electric charge of one of the spheres. I'll reset the parameters of the experiment for you. To change the charge of the sphere connected to the tension source, change the voltage of the source. The higher the voltage, the more charge the sphere will have. Hit the record button to record your measurement of the electrostatic force for that charge. Once you have recorded 3 different data points, we will obtain a tendency line. Record 3 values of the electrostatic force for 3 different values of the charge. Our graph is a straight line. That means that the force is directly proportional to the charge of the sphere on the scale. What do you think the graph will look like if we change the charge of the other sphere? This question is not graded. Let's find out if our hypothesis is right. I have reset the parameters of the experiment. Connect the second sphere to the source and measure the electrostatic force for 3 different values of the second sphere's charge. Disconnect the sphere on the scale from the power source. Connect the sphere on the measuring rod. Record 3 values of the electrostatic force for 3 different values of the charge. Look, we got another straight line. Our hypothesis was right. The electrostatic force is directly proportional to the charge of both spheres. I'll keep the graph in the Media tab so that we can look at it whenever we need it. We have obtained graphs for all 3 variables of our experiment. We can now look at those graphs in the Media tab. We can also keep using this setup to check the value of the electrostatic force for different values of the charges and distance. These are really nice graphs, and they give us a visual idea of how the electrostatic force changes with each parameter, but I wish we could sum all that up in an equation. If my database is up to date, there should be a file on the big screen to your right showing precisely that equation, but it seems to have one of those "prove you are human" locks. I'm afraid I can't hack it. Could you help me with this? Move to the big screen to your right. It seems we need to sort out these different factors by their effect on the electrostatic force. Aha! The data we just gathered in Coulomb's experiment should allow us to do just that. Classify the variables on the cards by their effect on the electrostatic force. Well done! The magnitude of the electrostatic force is directly proportional to the charge. Well done! The magnitude of the electrostatic force is directly proportional to the charge. Exactly. The further apart the charges are, the weaker the electrostatic force between them. Amazing! You have unlocked the equation of Coulomb's law. We can use this equation to calculate the magnitude of the electrostatic force. Let's see what it says. The electrostatic force between the 2 particles is directly proportional to their charges, so the charges Q1 and Q2 show up multiplying in the numerator. For now, we only care about the magnitude of the force and not its direction, so we consider only the amount of charge and not its sign. That's what the little bars on the sides of Q1 and Q2 mean. The electrostatic force decreases with the distance between the charges squared. That's why R appears squared in the denominator. If you recall Newton's law of universal gravitation, the gravitational force decreased with distance in the same way. We call laws that change with distance in this particular way inverse square laws. Remember that the distance between the spheres is measured from their center. Lastly, the k in this equation is simply a constant of proportionality. It makes the numbers add up for a given unit system, but it doesn't add any physical meaning. Let's put this equation to use. What do you think will happen to the electrostatic force between 2 charged particles if we double one of the charges? Well said! The electrostatic force is directly proportional to the charge, so if a charge changes, the electrostatic force will change in the same proportion. What will happen to the electrostatic force between 2 charged particles if we double the value of both charges at the same time? Precisely. The electrostatic force is proportional to each of the charges, so if both double, the electrostatic force will be multiplied by 2 twice. That is, it will end up multiplied by 4. What will happen to the electrostatic force between 2 charged particles if we double the distance between them? That's right. Coulomb's law is an inverse square law. That means that, if the distance between the charges is multiplied by some number, the force will be divided by the square of that number. Now that we know how to calculate the magnitude of the electrostatic force, it is time to talk about its direction. To do this, let's go back to the experiment on Coulomb's law. Go back to Coulomb's experiment. Select a negative voltage on the tension source and observe what happens to the charge and to the reading on the scale. Look, this source has a neutral ground reference, so, by connecting a negative voltage to the sphere, we are giving it a negative charge. The scale here is not measuring the weight, but the electrostatic force acting on the sphere on top of it. Before, the force was pushing the sphere down, so the scale had a positive reading, but now, the electrostatic force is lifting the sphere, so the reading is negative. This is because the electrostatic force can be either repelling or attractive depending on the sign of the charges. In fact, the force acts along the line joining the two particles. Like charges repel, and opposite charges attract. Let's see what the rule of the signs means in practice. Move to the big screen again. On the screen, you have two charges that exert an electrostatic force on one another. Click on each charge to select the direction of the electrostatic force it experiences. Careful! Remember that the electrostatic force acts along the line joining the two particles and that charges of the same sign repel, while charges of opposite signs attract. Let me clear the wrong answers for you so you can try again. Well done! This is exactly right. The charges have opposite signs, so the electrostatic force is attractive. It pulls the charges closer together. Let's try something a bit trickier this time. Click on each charge to select the direction of the electrostatic force it experiences. Well done! This is exactly right. The charges have the same sign, so the electrostatic force is repulsive. It drives the charges apart from one another. You are ready for a harder challenge. Click on each charge to select the direction of the electrostatic force it experiences. Amazing! Right on! The charges are on an oblique line, so the force acts along that same oblique line. They have the same sign, so the electrostatic force is repelling. Don't let those cute smiles fool you. These little guys don't want to hang out together. Now on to the final challenge. We will put together everything we have learned and predict the magnitude and direction of the electrostatic forces between two charges. Are you ready? The particle on the left has a negative charge Q1 of 2 nanocoulombs. The particle on the right has a positive charge Q2 of 3 nanocoulombs. They are separated by a distance r of 3 centimeters, and Coulomb's constant K is 899 times 10 to the 9 Newton per meter squared Coulomb squared. What is the magnitude of the electrostatic force between the charges? You may need pen and paper for this task. Great use of the equation of Coulomb's law. We are almost there. Now, let's analyze the direction of the force. You will see 4 different images where the electrostatic forces on the charges are drawn as arrows of different sizes. Select the image that better represents the physical situation in our problem. Select the image that better represents the electrostatic forces between the charges. The arrows point in the direction of the force, and they are longer the stronger the force. Not quite. The electrostatic forces between the two particles are an action-reaction pair. What does that mean for their magnitudes? Right on. The electrostatic forces are attractive because the charges have opposite signs, and both forces have the same magnitude. Great job! You have mastered Coulomb's law and the electrostatic force. With what we have learned, I can tell that powder coating must work like the particles in our last problem. The powder and the surface stick together because they have opposite charges, so the electrostatic force binds them together. You know what? I think I'll stick to this look for a bit longer. Holographic finishes are cool, but classic Dr. One is even cooler. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.